Hello, welcome to part 2 of my series on the quantum mechanical harmonic oscillator. In this video we're going to solve the exact wave function for the ground state, so we're going to be solving for A. We're also going to find the wave functions for the first and second excited states, and I'll also introduce to you harmonic polynomials. And by the end of the video I'll show you an animation that illustrates the wave functions and the eigenvalues of the harmonic oscillator. So, in the previous video, we solved the differential equation and it gave us the wave function for the ground state. And if we graph it, we can see it has a nice smooth peak. Okay, and this is a Gaussian curve. So, solving for A, the wave function must be normalized. Okay, like we've done in the videos on the particle in the square well. We normalize the wave function, so therefore we can say that 1 is equal to the integral from negative infinity to infinity, or whatever your boundaries happen to be, in this case the infinities, and we have the probability amplitude squared of our wave function with respect to x. Okay, so it's basically saying the total probability of finding a particle anywhere in this region in space is 1. Okay, it exists somewhere. Right, so all we need to do is substitute our wave function. So therefore we get 1 is equal to a squared multiplied by the integral from negative infinity to infinity of e to the power negative x squared divided by 2x naught squared, okay, and all of that is squared dx naught. Okay, now I won't solve this integral, okay, it's a very tricky integral, but anyway, the solution to this is simply a squared pi to the half x naught. Okay, so it's nice and simple. Now, what we have to do now is say, well, that's equal to 1, isn't it? So solve for A. A, therefore, is going to equal 1 over pi to the quarter, and then we have x naught to the power half. And we've solved for A by normalizing the wave function. Okay? So this means the wave function for the ground state of a quantum mechanical harmonic oscillator is this, in completed form. Right, so now we're going to find the first excited state, okay? So the wave function. So as we know before, the wave function for the first excited state, okay, it's obviously the inner product of x with 1. Okay, 1 is the first eigenstate. And we know, using the creation operator, that 1 is equal to a dagger acting on the ground state. Okay? So, and we know, actually, that the creation operator is equal to 1 over x naught to the times the square root of 2. Then we have our position operator, negative x naught squared d dx. Okay? So therefore, psi 1x, okay, is equal to this. We just put in the creation operator, like so. Okay? So what's this equal to? So we have x a dagger naught is equal to 1 over x naught square root of 2. Okay, and then we have x, put in the creation operator, which was x negative x naught squared times the derivative, like this, and that's with the ground state. Okay. And then this is equal to 1 over x naught root 2 multiplied by x minus x naught squared times the derivative, and then we have x naught. Okay. Good, and as you might be able to see, psi naught x is equal to the inner product here, x and the ground state. And so therefore, psi 1x is going to equal 1 over x naught root 2 times x minus x naught squared times the derivative with respect to x of psi naught x. Okay, so we can therefore simplify it slightly. We have psi 1x is equal to 1 over x naught root 2, and then we have x negative x naught squared, and then we multiply by negative x divided by x naught squared, and then we have our wave function. Okay, right, so all of this, as you'll be able to see, is equal to root 2 divided by x naught multiplied by x times psi naught x. Okay, so psi naught x, as we had, if we remember, psi naught x was equal to 1 over pi to the quarter x naught to the half times e to the power negative x squared divided by 2x naught squared. Okay, that was the ground state wave function. So therefore, we know psi 1x is equal to root 2 divided by x naught x psi naught. Just put this into here. And so therefore, we find the wave function for the first excited state, and that is equal to root 2 divided by pi to the quarter multiplied by x naught to the power 3 halves times x times e to the power negative x squared divided by 2x naught squared. And there we go. The wave function for the first excited state. So you can see when we graph psi 1x, it has one node. Okay, a node is a transition to the x-axis. Okay, it now has one peak and one trough. Alright, so now we're going to find the second excited state. Okay, so we can find the second wave function, okay, using this formula. Okay, 1 over square root of 2 factorial, then we have x, then we have our creation operator, squared, and then our ground state. Okay, we looked at that in part 1. Okay, so substituting for a dagger, the equation therefore becomes psi 2x is equal to 1 over root 2 factorial, and then we have 1 over 2x naught squared multiplied by x minus x naught squared ddx. Of course, that acts on the wave function psi naught x. Okay, good. To solve this general differential equation, you make use of the fact, this is quite long, that x minus x naught squared ddx to the power n, I'll explain this in a minute, multiplied by e to the power negative x squared divided by 2x naught squared is equal to e to the power of negative x squared divided by 2x naught squared, as usual. Okay, and we then, that's in brackets, and then we have hn times by x divided by x naught. Okay, I hope that makes sense. So we can solve the differential equation knowing this, where h(n)x, okay, is the nth Hermite polynomial, okay, which is defined in this way. We have -1 to the power n times e to the power x squared times dn divided by dxn times e to the power -x squared. Okay, I suggest you write notes on this. So, what do the Hermite polynomials look like? Well, here's h0x. h0x is 1, okay? h1x is equal to 2x. h2x is equal to 4x squared minus 2. h3x is equal to 8x cubed minus 12x, and so on. You can actually look these up. But these are the first 4 Hermite polynomials. So what does this buy you? You can express the wave functions for quantum mechanical harmonic oscillators like this using Hermite polynomials. Okay? So, therefore, we can say that the wave function psi nx of any state is equal to, bear with me, 1 divided by pi to the quarter multiplied by 2n n factorial x naught all to the power half. That's all divided by 1. Then we have our Hermite polynomial, which in total looks like this. There we have it. Okay? So this is the wave function for the quantum mechanical harmonic oscillator using the Hermite polynomial. Okay? Where, as we know, I'll just remind you, x naught is equal to h bar divided by m omega all to the power half. So this is the wave function for the second excited state that we calculated, and we graph it. We can see now it has 2 nodes and 2 peaks and 1 trough. So the preceding section gives you psi n of x, and you've already solved for En, the eigenvalues, so you're on top of harmonic oscillators. Now let's look at an example. Say that you have a proton undergoing harmonic oscillation, okay, with the angular frequency omega equaling 4.58 times 10 to the 21 seconds. Okay, so you have a proton and it's oscillating back and forth, okay, with the angular frequency given here. Okay, what are the energies of the various energy levels of the proton? So you know that in general, En is equal to n plus a half h bar omega, as n goes from 0, 1, and 2, and so on. Okay, so here are the energies of the proton in megaelectron volts. E0 is equal to h bar over omega 2, which is equal to 1.51 MeV. We have E1 is equal to 3 h bar omega divided by 2, which is 4.52 MeV. E3, so I should say E2, is equal to 5 h bar omega divided by 2, which is 7.54 MeV. And then we can say, finish off with E3, and that's equal to 7 h bar omega divided by 2, and that is 10.6 mega electron volts. Okay, and so on. So, what about the wave functions? So the general form psi n of x is given here, okay, as we calculated before, where x naught is equal to h bar divided by m omega to the power half. So therefore, x naught is equal to 3.71 times 10 to the negative 15 meters. Okay? If we convert all length measurements into femtometers, where 1 femtometer is equal to 1 times 10 to the minus 15 meters, giving you x naught is equal to 3.71 femtometers. Okay? So, here's psi naught x, where x is measured in femtometers. Psi naught x is equal to 1 over 1.92 pi to the power quarter e to the power negative x squared divided by 27.5. And here are a couple more wave functions. So there's an example of a proton undergoing harmonic oscillation. So now let's look at the animations. So here we have a fantastic animation for our wave functions we calculated and our energy eigenvalues. Okay, so we can see that in the ground state we have our single peak and our lowest energy state. Okay, if we move it up to the first excited state, we move up to our energy eigenvalue of 3 over 2 h bar omega. Okay, and then we continue to state 2, state 3, state 4, state 5, 6, 7, 8, 9, 10. And you can see they oscillate more rapidly. We can also look at the probabilities, okay, our probability amplitude squared. And we can see that as the quantum number increases, the energy of the wave functions is greater, it oscillates greater, and it's more spread out, as you can see. Okay, so let's look at a step-by-step explanation. So here we have our ground state. Even though the ground state has a quantum number n equals 0, the lowest possible energy, E naught equals h bar omega 2, the so-called 0 point energy, is greater than 0. For a particle confined to a localized region of space, the uncertainty principle requires the particle to have a minimum unavoidable kinetic energy. The energy eigenvalues of the harmonic oscillator are equally spaced. Thus, the difference in energy between adjacent energy levels is equal to h bar omega. This is called the transition energy, and we've already calculated that in the part 1. The spatial part of the energy eigenfunctions have the general structure psi nx equals a constant times a polynomial in x times a bell-shaped Gaussian function. The greater the quantum number n, the greater the number of maxima and minima of the polynomial, and the greater the effective range of the energy eigenfunction. This is similar to a classical oscillator, whose range increases with increasing energy. The Gaussian, e to the power negative m omega x squared divided by 2 h bar, leads to the energy eigenfunction decaying quickly at the ends of its range. The ground state energy eigenfunction just equals a Gaussian function, the polynomial being a constant in this case, as we've already seen. Due to the de Broglie relation, momentum equals h divided by the wavelength, the kinetic energy k equals p squared divided by 2m of the quantum particle can be seen graphically as the curvature of the wave function. The greater the kinetic energy of the particle, the shorter the wavelength lambda of the wave function. For a given n, the quantum particle has a maximal kinetic energy, the shortest wavelength, at the equilibrium position, and a lower kinetic energy, so a longer wavelength, close to the turning points. Note that the total energy is independent of position for a given n. At the classical turning points, all energy is potential energy. Okay, and I'll remind you, n is the quantum number. A classical particle oscillating on a spring would move fastest when passing through the equilibrium position x equals 0, and momentarily come to rest when reversing direction at the turning points. If we choose a random time to look at the position of the oscillator, we are most likely to find it at the turning points, and least likely to find it at the equilibrium position, as it spends least time here. The classical probability density shows this behaviour, being minimal at x equals 0 and tending to infinity at the turning points, as you can see here. Okay? For the quantum oscillator, the energy eigenfunctions and probability densities extend beyond the classical turning points. There is a finite non-zero probability of finding the particle beyond the classically allowed region, so beyond the turning points. For large values of n, the quantum mechanical probability density, when spatially averaged, approaches the classical probability density. So in contrast to the classical oscillating particle, the quantum particle in an energy eigenstate described by psi x is not bouncing back and forth with time. Instead, the particle is smeared out over the entire range of the energy eigenfunction at all times. A classical particle has a given position at a fixed time, even if we do not know this position. This is not any more true for the quantum particle. And there you have it. Okay, so the red line is our classical probability distribution, as you can see. So in the last video covering this series, we're going to look at harmonic oscillator operators as matrices. I'll see you in the next video.